These are the notes on motion. This will be the beginning of a new unit. Physics is the study of motion, energy, and forces acting on matter. So a lot of what physics concerns itself with is how things move and what causes them to move or change their motion. So that's what we're getting into now. We're going to get into some of the things that cause an object to move, and those are the forces, and how exactly that works. This is a major component of physics. Now, some of the things might seem very obvious to you, so just bear with me. Other things will seem a little more complex. So it's a mixed bag. What we're going to start off with is the way that we talk about motion and the words that we use in science. So when we talk about motion, we sometimes do it with words. Sometimes we use motion diagrams, which are little pictures showing objects and where they're located, and we use graphs. We're going to need to use certain terms, not just any word you want, like position, distance, and displacement, and time interval in a scientific manner to describe motion. Most of the time, we have to describe motion with respect to time. Otherwise, it's kind of hard to describe what's going on. We also need to pick a reference. We need to pick a place to start. Even the simplest form of motion, movement along a straight line, or what we call linear motion, has a few requirements. A description of motion relates to place and time. Okay, we also call that space-time. So you must be able to answer the questions of where and when an object is positioned to describe its motion. You need to know when it was in various positions. In the figure below, the car has moved from A to B in a certain time interval, time period. So we can determine some things about the way the car is moving just from those pieces of information alone. So this is a motion diagram that you're seeing here. So the car is moving toward the right. We're marking the position at the middle of the car. That's often what we use. You could do either the middle or the front of the car, as long as you're consistent. If it's a solid object, you can mark any position. Typically, we mark what is called the center of gravity, the center of mass, which is near the middle, and it moved from A to B over that time interval. Here we see a runner moving to the right at what we call a constant velocity. So every interval, which is every new picture, the runner moves the same amount. If you take the center of the runner as your position, notice how those dots are evenly spaced out. Now, if we want to get quantitative, which of course we do, then we need to begin to use numbers. We usually use the metric system, so let's measure the distances in meters. So if this runner is running along that axis right there, that x-axis, it's a pretty obvious axis to have because it's a linear kind of motion in one direction. There's no question about where you're going to start because you're going to start with 0 when your time begins. Okay, so we're choosing to start the runner at 0 because that's the most convenient, and that's when we begin to count off, let's say, the time. We also need a time graph. We need a time axis, and let's say we're measuring in seconds. It doesn't say that in this particular diagram, but if each position is every second, that would give us our time axis. And you can tell how far the runner has made it from the initial position of 0 by measuring along the axis. And we like to put little arrows in physics. It's a very typical thing. We'll talk about those in a moment. We like to measure how far the runner has traveled at various intervals. So see those green arrows, that indicates that at one point the runner had traveled from 0 to 10, had traveled 10 meters, and that at another point had traveled from 0 all the way over to 30, or 30 meters. So the length of those arrows indicates the distance that the runner has traveled at that particular time. Okay, so measuring from the origin to the position of the runner tells you the distance that they have traveled at that point in time. So if an object were located to the left of where you started and the runner is moving to your right, well, that would be given a negative value. So just like on any graph, if you go past your 0, well, you begin to measure with the same scale into the negatives. But now that we're going to be getting quantitative, it's important to differentiate in physics between the two kinds of quantities that you can have. One quantity that you might have might be a vector. A vector that has a size or magnitude and a direction is called a vector. And those you can easily represent with an arrow based on the scale of your diagram or graph. But there are some quantities that are really just numbers without any particular direction, such as distance, time, or temperature, and those are called scalars. So you could say 30 meters, but that doesn't tell me 30 meters in which direction. So that alone would be a scalar. But if I were to say 30 meters north, well, then you know which direction that's going. That would be a vector. So you've got to differentiate between these in physics because in certain situations you might need one or the other. Whenever something is an important concept like this, I always make these little call-outs. So obviously you've got to know what a vector is and you've got to know what a scalar is. And that's going to be coming up quite a bit in this unit. So remember, the vector has direction and the scalar does not. When we have vectors, you can actually add them together graphically, but you got to make sure that your vectors are drawn correctly. They've got to be using the scale of your diagram. So it's important to have a scale to begin with, make it consistent across your graph or diagram, and then it's actually very easy to add vectors just looking at them on paper. Okay? It's important to choose a scale where your 5 centimeter long vector or 10 centimeter long vector is going to be a significant part of what you need. You don't want vectors going off your page, so you got to choose your scale appropriately. So vectors can be added. You can get the sum of two vectors, which is really easy to do visually. For example, we have this diagram here, which is obviously on a very small scale. These would obviously be toys, like a model of a town. And to go from the house to the store is 5 meters. Then to go from the store to the ant's house is 2 meters more. So clearly you can add those vectors simply by putting the tail of one arrow at the tip of the other, and then putting a new vector, which is called the resultants, which runs the entire length. This is very similar to just regular addition, but you're going to see that sometimes, depending on when things get more complicated, it might be easier to add them in the form of vectors than simply adding up the numbers on paper. So the resultant always points from the tail of the first vector to the tip of the last vector when they are added together. Just like it's important to measure your distance from a chosen position or reference point, it's also important to measure time consistently using a time interval. That could be seconds, that could be minutes. You've got to make sure that you're measuring time consistently. The common symbol for a time interval is delta t, where the Greek letter delta, which is a little triangle, is used to represent the change of something. So delta t would be the change of time between each interval. Another quantity that we can measure is called displacement, or delta d, and we have to choose the time interval we're going to measure it over. So notice the green arrow on the diagram going from when the runner is at position 5 meters to position 25 meters, moving to the right. We can measure that he has moved 20 meters to the right, and that is his delta d, his displacement. Vectors can also be subtracted if you have two vectors, a and b, and you want to subtract a minus b. Well, then you simply reverse the direction of b, exactly opposite, but the same scale, the same length. So put the tail of b at the head of a, and where the head of b winds up is what you call your resultant. It's a lot easier to see visually than it is to say in words, but you can see that it's exactly the subtraction of b from a that gives you the resultant a minus b. Here's another example of subtracting vectors. Now in physics, we a lot of times use the little letters below the subscripts to indicate whether something is where you started or where you ended. df indicates the final displacement, and di represents the initial displacement. Well, if you want to know how much displacement occurred over your time interval, you need to actually subtract the initial position from the final position to make sure you're only getting the change that has occurred. So we very frequently do df minus di, and we wind up with delta d. So notice that in order to do that, we have to reverse the direction of di, put it onto the end, and what we get is the resultant, delta d. It's just like it sounds mathematically, but you can also do it visually using the arrows, which is sometimes easier. It might not look easier right now, but it can be. So motion diagrams, that's the way that we show how things are moving. Sometimes it's a little bit cartoony, but it always has to be to a consistent scale. So in other words, on your paper, whatever, a centimeter needs to equal something in the real world, like a meter. Here we see two runners. Let's say that we started off with time interval being 0 right there, and then after our next time interval, they have changed their positions, and then we have equally spaced time intervals. So now we can see that while the blue runner, has actually not started in the same position as the red runner. Therefore, if we want to measure how much displacement we have in the next time interval, we need to subtract where he was initially to get just the change. So that would be a reason for subtracting vectors. Also, you can see that they're not traveling at the same speed or the same velocity. We're going to talk about the difference of those in a moment. And so the displacement seen is different for the two different runners. So this is a great example of a motion diagram. And notice that we don't have to start them both in the same position. We don't have to start them both at 0. And our reference frame, we have to choose. So let's say it would be the left side of the picture. Okay, the very left side of the left picture could be our 0. But our 0 is chosen arbitrarily. It does not have to be a position of either runner. It just has to be a position that has been selected, a reference frame. So we could consider each runner separately. First of all, if this runner was in these 3 positions at our 3 photographs, obviously a photograph is taken at a moment in time, so that's why this is useful. And we can see that his position changes over time. However, if you want to measure his displacement, you have to always subtract his previous position. So you're always going to subtract the one that was before it. So it's going to be df minus di each time. The same thing goes with the red runner. Obviously those are photographs are taken at a moment in time, so those were her positions at those time intervals, and you would need to subtract her previous position, okay, from her final position. So again, it's df minus di in order to tell the displacement. And then if the time interval is consistent, you can use that to determine all kinds of interesting things. So vectors are things you can represent with arrows. Why can you represent them with arrows? Because they're going in a particular direction. That helps you remember what a vector is. Think of a vector as an arrow you can draw on a diagram. So therefore, it's got to point in a particular direction. So again, quantities that have both size, which is called magnitude, and direction are called vectors, and they can be represented with arrows. Quantities that are just numbers without any direction are called scalars, so you cannot represent them with an arrow. So think about it. If you can't represent it with an arrow on a diagram, it's a scalar, like a distance or time or temperature. Those are examples of scalars. This is when we start to get into our precise terminology in physics, because it is important the words we use, and I'll try to avoid slipping up and using the wrong word. I might do it occasionally, but when you're talking about displacement, that is a vector. When you're talking about distance, that is a scalar. For example, you could have 100 meters north and 100 meters south. That is a vector. But 100 meters is just a scalar. That could be in any direction. Get it? So vectors are useful for determining certain things, and scalars are also useful in their own way. But it's important not to sort of mix them up, and so we use a different term. Displacement and distance, very similar, but one of them is talking about in which direction. It is a vector. That is displacement. Distance can be measured in any direction, and there is therefore a scalar. Another example of vectors and scalars is velocity and speed. Now, a lot of people think, well, velocity is the fancy word, so you got to use that like all the time if you want to be more precise. But actually, no, speed is just as valid a term. It's just that speed and velocity are somewhat different. Although similar, they're somewhat different. Velocity is a vector. Speed is a scalar. So for example, you could be going 80 kilometers per hour. What is that? 80 kilometers per hour. That is a speed. You could be going 80 kilometers per hour south by southeast, and that is a vector. So the vector not only tells you the speed you're going, but it also tells you the direction, which makes it a velocity. So velocities are speed with direction. So it does mean something different. So please be careful using these terms. And again, it's a technical thing. I'll try to use the correct term in the correct place, but you might hear me slipping up occasionally if I'm just trying to put it into everyday language. Adding vectors can be done by taking the two arrows that are drawn to scale based on whatever your scale happens to be on your diagram or your graph, and then moving one of the vectors to the head of the other. Now this is for linear motion. This is the easiest way to do it. You wind up with the resultant. The resultant is the two vectors added together. So if you moved 5 meters to the right, and then you moved 3 meters to the right, and you added those together, your resultant would be 8 meters to the right. If you want to add vectors that are going in opposite directions, the same thing goes. You can still add them, and the resultant would be from the tail of one vector to the head of the other, the tip of the arrow. Just like this. So for example, if you went 5 meters to the right and then 3 meters to the left. Add those together, and what do you get? You get 2 meters to the right. So that would be the resultant of adding those vectors. This is also similar to subtracting. So obviously, if we had subtracted the first case when we had 2 moving to the right, and then we subtracted the second one, this would have been the result as well, obviously. So your assignment is fairly straightforward. You're going to be making some of these motion diagrams. It's a motion diagram assignment. Here's the instructions. You're going to draw 5 different linear motion diagrams, similar to the ones that you've seen in the notes, but each one needs to have a different scale. In other words, they can't all say 5 meters, 10 meters. You got to pick an appropriate scale for whatever we're observing here. The first one is an ant walking across a piece of paper. So that could actually be the scale of your actual paper. It doesn't have to be 1 centimeter representing 1 meter. It could just be 1 centimeter representing 1 centimeter. Then you can do a person walking across a soccer field. You have to picture an appropriate scale for that. I'm going to leave that up to you. A car driving down a straight road. All of these will be linear. They will just be moving to the right in a straight line, by the way. An airplane flying between 2 cities. So clearly we're talking about a different scale here. Make sure your scale is reasonable. A rocket in space going toward the moon. It would be an even bigger scale. What you need to do is indicate your time interval. So between each of the images you're showing, what is the time interval in between them? So for example, your time interval might be 1 second, or it might be 1 minute or 1 hour, whatever it happens to be for the scale. Make sure it's appropriate for the scale you're using. And then I want you to draw a displacement vector, an arrow, for the total displacement after the second time interval. So that will go from the origin to the second time interval. So not just one interval, but basically 2 of them. And it does not, you'll see in my example where I've located it, you can either put it directly on your axis or you can offset it as long as it's the correct length. I want you to measure the delta t and the delta d on each diagram between the origin and the second interval. Well, that's just like the vector that you drew. So basically, you're giving me the delta d for your vector, the displacement, and the delta t for your vector. And we'll talk about that later, what to do with that in the following notes. Here's an example of what I'm looking for on this assignment. Okay, you don't have to be a great artist. Your pictures do not have to be realistic looking. They could just be little stick figures or representations of the moving object. Notice that the runner is moving in the time interval, which I'm indicating here. You have to write that, is 1 second. Every 1 second, he's moving the same amount of distance to the right. I would recommend doing that. It makes it much easier than doing anything else. I'm giving 6 intervals here. You don't need to do 6. You need to do at least 4. So starting with the 0, then do 4 more minimum. You can do 6 like this, or you can do minimum of 4. Notice I've drawn the vector, the green arrow pointing to the right, going to the second interval, right? So that is what I'm going to measure when I'm giving my delta d and delta t. For that particular vector, he has moved from 0 to 10, so it's df minus di, it's 10 minus 0, which is 10 meters. And then for the delta t, it would be 2 seconds because I've moved 2 of the time intervals. Okay, we will use those pieces of information later. Okay, so just make sure to have a clear diagram, and they can all be moving to the right. That's the standard. And at a constant velocity, you need to indicate your time interval. You need to have a vector like the green arrow. You need your delta d and delta t. So it's not too hard. The hardest thing is probably establishing what would be a reasonable amount of distance that would be moved, would be displaced each time interval, and also what your time interval would be. That's probably the hardest thing about setting up these diagrams. That is the end of the notes on motion. So now we know the terms to use, and then we're going to go from there. next time.